Okay, so let's crack on to why moles are useful. So, in the real world, we obviously do not go around counting the number of particles in the chemical we are using. It's never going to work, and 6 times 10 to the 23 is a really big number, and particles are really tiny. So how does this actually apply to the work we do as chemists? How do we work out the moles in a laboratory? Well, we're lucky that there's a relationship that exists. We've already said that 1 mole is equal to 6 times 10 to the 23 particles. But that also happens to be equal to the atomic or molecular mass of that particle in grams. So what we're looking at is if I had 1 mole of carbon atoms, that would mean I would have 6 times 10 to the 23 atoms, and that also equals 12 grams of carbon atoms. Because 1 carbon atom is 12, we can look up the atomic mass on the periodic table. So 1 atom is 12 relative atomic mass units, but 1 mole, 6 times 10 to the 23 atoms, is actually 12 grams of carbon atoms. So this means the mass of the chemical and the number of moles are related to one another by using the atomic mass on the periodic table. So as long as we have a periodic table, we can work out this conversion. So what is the conversion? They call me Mr. Mole. Mr. Mole wears a mass hat. So the relationship is often shown like this. MR, molecular mass or atomic mass, you could use the same, times mole with mass over the top in the usual kind of triangle we would use in maths to show mass divided by MR would give you moles, mass divided by moles would give you MR, MR times mole gives you mass. So this means if we know the mass of a chemical, we can use the periodic table to calculate the moles, or we could do the opposite. If we know the moles, we could work out what mass we've got. And this is really useful as long as you've got that periodic table in front of you, because most chemicals that we use in the lab, we can weigh, we can work out a mass of, so then we can use the number of moles. So if I had 24 grams of calcium, how many moles do I have? Well, calcium has an atomic mass of 40, so 24 divided by 40 would give me 0.6 moles of calcium. So nice and simple, mass divided by MR would give me the number of moles. If I have 0.6 moles of gold, what mass do I have? Well, going back to the same triangle, we would do the MR times the moles to get the mass. So gold has an atomic mass of 197, so 0.6 times 197 is 118.2 grams of gold. Now notice, guys, and this is where the importance comes in, we have the same number of moles here. We have 0.6 moles of gold, we have 0.6 moles of calcium, which means we have exactly the same number of particles. However, the mass is very, very, very different, because gold is a much bigger atom, contains a lot more protons and neutrons, so it's much heavier. And this is why we need moles, because if we wanted exactly the same number of atoms of gold as we did of calcium, and we weighed out 24 grams of gold, we are not going to get the same number of particles because gold weighs so much more. So we have to compare them with moles to know that we've got the same number of particles. So our calculations work the same way with compounds. You just have to calculate the MR first, like we did back in the atomic theory topic. Remember adding up the atomic masses to make the molecular mass. So you would add together all of the atomic masses of all of the atoms in the compound or molecule to get the MR. And we're still using our Mr. Mole with his mass hat on, okay? So if I had 12 grams of sodium hydroxide, how many moles do I have? Now this is, sodium hydroxide is something we commonly use, so we could work this out. So 12 grams of sodium hydroxide, well, we know sodium weighs 23 from the periodic table, oxygen 16, hydrogen 1. We add those together because there is 1 of each, so we get an MR of 40. We would do 12 divided by 40, which gives us 0.3 moles of sodium hydroxide. Why is this useful in the lab? Well, once we know we've got 0.3 moles of sodium hydroxide, we can work out how much of other chemicals we need to react with it. Because we don't want to waste chemicals in the lab. We're looking at keeping the amount of chemicals used to a minimum. So if we were saying, okay, we're going to do a neutralization, we're going to react sodium hydroxide with hydrochloric acid in this neutralization. We know our equation, we've done this before, so 1 sodium hydroxide plus 1 hydrochloric acid makes 1 sodium chloride plus water. And we know it's balanced, so we're saying here for 1 sodium hydroxide we need 1 hydrochloric acid because it's balanced, okay? So for every one of these particles, I need one of these particles. So what mass of HCl would we need? Well, if we know 1 reacts with 1, if we have 0.3, we're going to need 0.3, the same amount. So we would then work out, if we got 0.3 moles of HCl, what mass would that be? Because then we could weigh out how much HCl we need and we wouldn't be wasting any chemical. So we would work out hydrogen 1, chlorine 35.5, so HCl is 36.5, 0.3 times 36.5, we need 10.95 grams of HCl. So this is mostly what we use moles for, guys. Because if we assumed everything had the same number of particles, the same mass, I would weigh out 12 grams of sodium hydroxide, 12 grams of hydrochloric acid, and I'd actually be wasting slightly over a gram of the hydrochloric acid because those particles wouldn't be needed. But by checking with the number of moles, I can work out how many grams I actually need.